Alrighty everyone, I'm recording a quick bonus video to show you a shortcut method that I stumbled upon earlier today when I was writing my lecture notes for the in-person lecture on Method of Undetermined Coefficients Part 3. Now, Method of Undetermined Coefficients Part 3 covers what we do when our initial guess at a particular solution ends up failing because our particular solution, that guess, happens to be actually a complementary solution. And in today's video / lecture, we said, okay, the fix for that is to take your initial guess and multiply it by an x. So in this video, what we're going to see is a shortcut method that can be used to find the unknown coefficients in yp under those circumstances. For a motivating example, let's consider the following problem. We want to solve, or at least find yp for the equation y double prime plus 9y equals 7 cosine of 3x. Now, if I were going to get started solving this, the first thing that I would do is I would find y sub c. And if I do that, I pass to the complementary equation, and I guess a solution of an exponential format, and I look at the corresponding auxiliary equation, then the roots to the auxiliary equation are the two complex numbers plus and minus 3i. So that means that our complementary solution is the form any number times cosine of 3x plus any number times sine of 3x. Now that I've found y sub c, I'm going to return to the problem at hand, which says, what is a particular solution? What is y sub p? Now, the function on the right side is of trigonometric format. So my inclination would be to guess a particular solution of a similar format. My original guess at a particular solution, yp, would be some number times cosine of 3x, to match this 3x on the right side here, cosine 3x, plus b sine 3x. But we can already see that this guess is going to be cursed. It's not going to work out because our initial guess coincides exactly with our complementary function. So we already know if we plug this guess into our ODE, then it will be equal to 0, not 7 cosine 3x. So what we would have to do is we would have to modify this guess. We would have to do a new guess where we take the old guess and multiply it by an extra copy of x. Then we would have to go through the hassle of finding yp single prime and finding yp double prime, being very careful at each stage to make sure that we're using product rule and chain rule correctly. So there would be a lot of work to do in those steps, and lots of opportunity to make mistakes. So instead of doing all of that process, let me go ahead and show you a shortcut method which uses some of the results that we got all the way back in video 21 when we talked about fast reduction of order. To set the stage, let's suppose that we have some initial guess at a particular solution that I might just call yp0, p for particular, 0 because it was our initial guess at a particular solution. But as it turns out, your yp0, your initial guess at a particular solution, turns out to be a solution to the complementary equation. If you plug it in, you get 0 as a result. Suppose that that's true. Well, we saw back in video number 21 that if you have a solution to a homogeneous ODE, like yp0 in this example, and you multiply by that function by something else called u, and you plug it into this expression on the left side, when we were in video 21 and we did that simplification, we got the following result. We found that under those conditions, the left-hand side of the ODE simplified to this expression here that I have boxed in pink. Now in this context, y1 is what we called the solution to the complementary equation. In our problem, we're calling it yp0, but all the algebra works out the same. It's just that the notation was slightly different. So I've gone ahead and copied that expression here, updating it to match the notation of our current situation. Now this formula gives us a very, very convenient shorthand for what we get when we plug something like, for example, x times our initial particular solution, guess, into the left side of the differential equation in our problem. In our motivating example, our initial guess at a solution was equal to a cosine 3x plus b sine 3x. And we multiplied it by x. Now, when we plug x times p sub 0 into the differential equation in our problem, let's use the shortcut formula to figure out what expression we would get. Now, in our problem, y double prime plus 9y, the quantity called p of x, which is multiplied by the first derivative, would be equal to 0 because there is no y prime term. In order to fill in the remaining blanks in this shortcut formula, I still need to figure out the identity of u prime, u double prime, and yp0 prime. So let's go ahead and get those values. For this u prime would be equal to 1, u double prime would be equal to 0, and the derivative of our yp0 prime would be equal to negative 3a sine 3x, positive 3b cosine 3x. Now let's go ahead and take all of this data and plug it into this shortcut formula. This shortcut formula tells us what the expression on the left-hand side of our differential equation would become if we plugged in this yp. So let's see what we get. U double prime is 0. So since u double prime is 0, this entire first term in the shortcut formula vanishes. U single prime is 1. So we're just going to get 2 times yp0 prime and then p of x times yp0, but because p of x is equal to 0, that term will vanish as well. That's the left-hand side of the differential equation, and the right-hand side of our differential equation in our problem is equal to 7 cosine 3x. So let's copy that down on the right side of the equal sign. Now our mission is just to examine this equation and find the values of a and b which make this equation true. So for example, by comparing the sign terms on both sides, I can conclude that negative 6a must be equal to 0 because we don't have any sign terms on the right. By comparing the cosine terms, I can conclude that 6b must be equal to 7, and therefore b must be equal to 7 over 6. So I have now obtained the values of a and b, which are applicable to the adjusted guess yp equals x times the quantity a cosine plus b sine. If I fill in these blanks with the a and b that we just found, I get the following result. The true particular solution would be equal to x times the quantity. Well, a was 0, and as a result, there is no cosine term. There's only a sine term with a coefficient of 7/6. So that is how the shortcut can be used to find the particular solution. We had our initial guess at a particular solution, but it turned out to be one of the solutions to the complementary equation. So we had to modify our guess by multiplying it by an extra copy of x. By taking our initial guess at a particular solution and taking our multiplied quantity, which was called u, and plugging those into this shortcut formula, we very quickly got the left-hand side of the differential equation, which we could then set equal to the right-hand side of our differential equation to find the values of a and b, which are appropriate for our particular solution. So this can save quite a bit of time. You can also use this technique in situations where you might have to modify your guess by applying two x's instead of just one. For example, here, if I look at this problem and I start by considering all the complementary solutions, then with my standard exponential guess, I get an auxiliary equation with a repeated root of r equals 3. So my complementary solutions have the form number times e to the 3x plus number times x e to the 3x. Now if I look at this expression on the right-hand side, 7e to the 3x, my initial guess at a particular solution would be of the form number e to the 3x. But I can see that that guess will not work. And I can also see that multiplying by a single additional factor of x will also not work. So my sort of true and final guess at a particular solution would be x squared times my initial guess, x squared times a e to the 3x. So in my problem, what I would call u is the quantity x squared that's being multiplied by our initial guess, yp0. In our problem, the quantity p of x, which is multiplied by y single prime, would be the constant -6. yp0 prime, the derivative of our initial guess, would be 3a e to the 3x. U single prime, the derivative of x squared, would be 2x, and u double prime would be 2. Now let's take all of that data and plug it into the shortcut formula that we have for the left-hand side of our differential equation. U double prime would be 2, and that would be multiplied by, let's review our shortcut formula. U double prime is multiplied by our initial guess. So u double prime is multiplied by a e to the 3x. And then we have plus u single prime plus 2x multiplied by the quantity 2 times yp0 prime plus p of x, which is -6, times yp0. That's the left side of our differential equation, and on the right side, we want it to be equal to 7e to the 3x. Now notice that these two terms in the brackets are opposites, so these completely cancel each other out. And I'm left with the simple equation 2a e to the 3x is equal to 7 e to the 3x, and as a result, a must be equal to 7 over 2. So if I put that value of a into this formula, for my actual real guess at a particular solution, I get the following result. Yp, the true particular solution, would be 7 over 2 times x squared e to the 3x. So that's the shortcut formula. It's a little bit niche. You can't use it in a lot of situations. You can only use it in this situation where your initial guess for a particular solution fails because it happens to be one of the solutions to the complementary equation. But when you can use it, it's very nice to use it, especially in situations like this motivating example with sine and cosine. It can save a lot of time.